can do an antiderivative twice, regardless of what universe you live in, right? Not only can you recover it, as long as this is constant, as long as the acceleration of gravity is constant, your position function will always be what type of function? Quadratic, right? Because you got an antiderivative twice. So the first time you go constant, your first antiderivative gives you a linear function. Where is it? There, right here. That's your linear. That's our velocity function, right? It's a linear function in t, and then when you go to the antiderivative one more time, you have a quadratic function in t. So for all planets in the universe that have a constant acceleration of gravity, which most would because they're not changing their mass, they're just there, then you can guarantee that the position function for an object falling on that planet would be a quadratic function, regardless of what alien species you are, right? It should be quadratic. It's kind of interesting, yeah? Questions?
Did you have to have the acceleration without accounting for like wonders or anything like that, essentially taking all the air out?
Yeah, you have to take, that formula only works without air.
So you just have to have acceleration first, right, of that planet? So
You have to be able to measure the acceleration of gravity on that planet, which can be done, you can do it with experiments, just like we do here,
okay.
right? It's an experiment that we have that number.
Just create a vacuum and measure it down.
Yeah, and maybe not every planet has atmosphere, so, you might not have to worry. So if you want to include the atmosphere, then then it gets a little more complicated.
Right.
Yes? Yeah, well, so what I wanted to do now is do an example with specific numbers. And so that was just kind of like, because y'all said y'all have seen this before, I just wanted to kind of like do a problem that I think has an interesting result. But let's do one that's more like actual numbers, and I'm not going to give you my acceleration function is not going to be a constant. It's going to be something else. So if a of t is, let's go with 12t squared minus 24t cubed, and I tell you that v of 1 is 8, and I tell you that s of 2 is 4, I want us to find s of t. So I give you the acceleration of some object at every point in time. I give you the velocity of this object at one point in time, and I give you the position of this object at one point in time, and you're supposed to be able to tell me the position of this object at every point in time. That's the way this works. Okay, so first things first, let's get velocity. So to get velocity, we need the antiderivative, right? The antiderivative of this. 4t cubed minus 6t to the fourth. So I'm not showing the steps here. Is that all right with everyone? I'm doing my power rule on this. What's the power rule on t squared? What's the antiderivative of that? T to the third with the 1/3 out front, right? So 1/3 t to the third. And then I multiply that by 12. I'll show it. Y'all are looking at me. Y'all are looking at me like. Okay, so it's 12 in front, and then it's 1/3 t to the third. That's the antiderivative of t squared. Minus 24, and then the antiderivative of t to the third is 1/4 t to the fourth. Plus c, some constant. Now, multiplying this together, that's the same as taking 12 and dividing by 3. That's 4t cubed. And then here, multiply those together. That's the same as dividing 24 by 4. That gives you 6. And then plus c. That's your velocity function. Did the sign-in sheet get around? Where's the sign-in? Everybody get that?
I think he's.
Okay. Anyone else? Pardon? Are those the papers? Okay. Yeah. Okay. Everyone's good? Okay, so everyone got their quiz back? Everyone signed in?
Sorry, he just needs his quiz.
Oh, quizzes. Here you go. All right, so what are we going to do now? We have the velocity function, but we have it as a family because we have plus c. We need the exact velocity function. So, but we know that v of 1 equals 8, right? Pardon me? Well, set it equal to 8, but we have to replace all the t's with 1s, don't we? Okay, so I'm going to replace the t's with 1s, 4 times 1 cubed minus 6 times 1 to the 4th, plus some constant, I don't know. That must equal 8. And because these are 1s, it's nice, right? So that's just 4 minus 6, that's negative 2. Negative 2 plus c is 8. So add 2 to both sides, you get c is 10. So I know exactly what c is now. So I have v of t equals 4t cubed minus 6t to the 4th plus 10. I have the velocity function. I'm not done with the problem, right? But at least I have the velocity function now. Now I need to go back one more antiderivative, and when I do that, I will have the position function as a family. I'll have another constant. No? Okay. All right, so for position s of t, all right, antiderivative again. So I'm going to go a little slow here. So 4 times here, antiderivative of t to the 3rd power, 1/4 t to the 4th. Okay, minus 6. Oh, shit. Okay, 1/5 t to the 5th, right? Antiderivative 10, 10t plus some constant. I'm going to use d instead of c so we don't confuse it with the other one. Crap. Can I just make the problem easier? Can I just make the problem easier? Oh, you already did it? You got a bunch of fractions and stuff in there? It's not too bad? Okay, I'll keep going then. I'll keep going. All right, so now we say, oh, let me clean it up. It's t to the 4th minus 6/5 t to the 5th? Okay, plus 10t plus d. That's where we are position-wise. Is this making more sense with actual numbers?
Yes.
Yeah? All right, so now I say, but I know that s of 2 equals 4. So when I plug 2 into that for t, I should get 4s. Or 4 is an answer. 2 to the 4th power minus 6/5 2 to the 5th power plus 10 times 2 plus d must equal 4. Y'all said y'all did that, and it was, it was not bad. Okay, so 2 to the 4th power is 16 minus 6 over 5 times 32 plus 20 plus d equals 4.
That's 38.4.
Oh, you just got a decimal on your calculator. Oh, okay, yeah. In that case, yes. Yeah, I mean, that's okay. I thought we were going to keep it as fractions.
192 fifths.
Yeah. All right, I'll keep going here. Let's see, let's do these two together. That and that, that's what, 36?
Yep.
Subtract 36 from both sides. What would you have? Negative 32? So I have negative 6/5. I want to stay away from that fraction for just a minute. Negative 6/5 times 32 plus d equals negative 32. That's where I am. And then, oh wait, hey, check this out. This just happens to work out this way. I'm going to add that fraction thing to both sides. So I get negative 32 plus 6/5 times 32, right? Isn't that what I have? I'll move that over like that. Just move that whole term over here, it becomes plus.
Oh, okay.
Yeah?
Yeah, it's
Yes, I could get my calculator, but I just got lucky on this. Look, this is, I can factor a 32 out of both of these. And if I do that, what's left here? -1. And what's left there? 6/5, right?
is this what happens when you're good at math?
And then how can I put these together? This is -5/5, right? So this is just 1/5. So this is 32 times 1/5, which is 32/5. Was that your answer? Yeah. Okay, either way, look, I mean, let's be honest with each other. At this point, this is just arithmetic, right? You're just solving for D. So yeah, it's a little messy, but this is not a natural way of doing this. I wouldn't expect anyone to do it this way. I just noticed that I could, so I did it. If these two numbers would have been different, then I would have been stuck with getting a common denominator and putting the fractions together. Yes?
Would it be a lot easier on the 16 minus 6/5? Yeah, on that one, like multiply everything by 5.
Oh yeah, you could have just cleared fractions in the very, there's all different ways we could have done this algebra, right? So whatever you're comfortable with. I mean, I'm just, once I get to here, I'm just kind of like, yeah, whatever, Yes?
So I'm sorry, what's the last thing you did right there?
Where? Here?
Yeah.
Put those together. So this, I rewrote -1 as -5/5.
Oh.
And then that adds together to get you 1/5.
You really just care about the calculus.
Yeah, it's just the antiderivative going backwards and then plugging in, knowing that you still need to like plug in something to actually lock down what that constant is. All right, we're going to go talk about some more stuff from 4.7. So in terms of antiderivatives, we've talked about the power rule, right? We just talked about how you can recover, you can go from acceleration backwards to get you back to position. But there's a whole slew of things that we need to know in this class in terms of antiderivatives, right? So the ones that we should know and be comfortable with at this point, the power rule, right? The antiderivative power rule. Antiderivative 1 over x and natural log absolute value of x. The antiderivative of e to the x is itself, right? All of these are with plus c. The antiderivative of cosine is sine, right? Because the derivative of sine is cosine. The antiderivative of sine, however, is negative cosine. And that has to do with the fact that when you take derivative of cosine, you get a negative. So you have to put a negative here to create a double negative so that you get a sine when you took the derivative. So I expect everyone here to be comfortable with these concepts.
And the right side
All
too.
in one doesn't have.
Oh, I'm not done. I'm not done. There's more, right? Then there's others, right, that you should know just because, again, you're experiencing Cal 1. We should all remember that in Cal 1, the derivative of tangent was secant squared. So the antiderivative of secant squared is tangent. We know in Cal 1 that the derivative of secant x is secant x tangent x, so the antiderivative of this is this. All the things that we kind of knew in the forward direction in terms of the trig functions are things that we should keep with us and take with us as we continue in this class. These two are big ones. Didn't we learn the derivatives of 6 of the inverse trig functions? There were 6 of them. There's only 2 that you need to burn into the brain. These 2, because we use them a lot. So the antiderivative of this is inverse sine. The antiderivative of that is inverse tangent. These 2 we won't use at all. Because I told you, hyperbolics were like their own little thing, and now we're just moving on. So I'd say on this chart, like everything except the hyperbolics, and then this first part over here is just properties of antiderivatives that if you have a constant, it comes for the ride. If you have 2 functions, you take the antiderivative each one separately. That's all that says. Yes?
Can we expect that we're going to have a problem similar to those 2
derivatives that you just mentioned, yeah, we'll
These
have
two?
to kind of see it, move it, manipulate it, and then end up with an antiderivative on the test.
Well, right now what we're saying is if you see this exactly, you need to know that the antiderivative is this. If you see this exactly, you need to know the antiderivative is that. That's all we're saying at this point.
Okay. I can just see a problem where we have to manipulate it to get it to look like that.
Oh yeah, we will. Yes, we will have to, that is coming, but just I'm saying at this point, you just need to at least know that those two go backwards to that. Yep.
So, I know that a lot of that comes on later with like series and things, but I never really thought about it before. At the early stage of doing like integration, can you really twist things arms to put them into the shape of inverse tangent, and then just take the integral of inverse tangent? Because I mean, it seems to me like it'd be pretty easy with most things to flip them, and then just subtract one. So I say like that x squared, and then you can just take that whole thing and just say, okay, now it's.
Well, the tangent one didn't have minus x squared, it had plus x squared. So I'm trying to understand what you're saying.
Well, what I mean is by
You're saying-
subtracting one, that gives you what x squared would be.
Not for tests.
So like,
I need to go to
I don't know, sorry, it's kind of a new thought, so it might be stupid, but. Think more on it.
Yeah, think a little more, formulate the question, because I'm trying to follow you, I'm not really following it, so think through it a little more. All right, we're moving on. So we are going to jump from here right into chapter 5 into the substitution rules. Is that a question?
Oh, no, it was a quick question regarding, so those trig antiderivatives, I don't think are on this sheet. So is there a place that you could like print those?
They are on the sheet. Let me, if I get through this first note, then I will be able to refer you to the sheet for all these things. So, because we need to change our notation. And I know a lot of you have seen this notation, but look at this, this idea that when we're given a function little f, that we want to find the antiderivative. Instead of writing it down like, hey, go find the antiderivative, we start using a new notation for it. So again, show of hands, how many of you saw this symbol here, the integral symbol, the antiderivative symbol in your Cal 1 class? Anybody? No? Never seen it? Never seen it? You saw? Okay. Anybody never seen it?
I don't remember.
Okay, so all this means, if we see this, this is the same as me asking you to find the antiderivative of that. That's all it means. So if I write this down, you basically look at that and say, oh, all I want to do is look at that right there, 2x. What's the antiderivative of 2x? So you'd use the power rule, and you'd say that's x squared. Agreed? Plus c. That's the notation we use. The integral sign, right? So this is all listed here. We have this right here. The whole thing together is called the indefinite integral. That symbol right there is called the integral sign. And I always tell my students, look at the integral sign as like a capital S that's been stretched out. And we will make sense of that later. Okay? Later on, we will explain why it's a capital S, and it'll mean a lot more later. For now, we just want to know what the symbol's called. F of x is the thing you're trying to find the antiderivative of. It's called the integrand. Dx, this part right here, which students always have trouble with, like, what is this part? It is called the differential. And what it does is it keeps track of what your variable is in the problem. So if our function is a function of x, this is saying that we're trying to find the antiderivative of this function, treating x like the independent variable. Later on, like in my Cal 3 class, we're going to have functions of several variables where our function might have x, y, z. And so when we find an antiderivative of a function of several variables, we need to know which one we're treating as the independent and which ones are not. So it means a lot later, and in this class it's going to be important as well, but for now, don't get yourself too bogged down with that dx. Now, capital F of x, that's the actual antiderivative that we find, right? Capital F of x is called the antiderivative. And then the c that we always add at the end is called the constant of integration. The process of finding antiderivatives of functions is called integration. So we are going to spend the next several weeks doing integration. All right, so our goal here is, can we start to find the antiderivative of more and more complicated functions? Not just the power rule, not just the things that you remember from Cal 1, like the antiderivative cosine is sine. So to answer your question about the formulas, right? If you go to your formula sheets, go to reference page 6. Everything you have, those are all the antiderivatives. So you know how you were asking me about the, like the tangent inverse and stuff? Look at formula number 17. Formula number 17 on our formula sheet says this. Antiderivative, it says du over a squared plus u squared equals 1 over a tangent inverse of u over a plus c. That's the same formula I put up on the board a second ago, except for us, didn't we have, it was like 1 over 1 plus x squared, and we said that the antiderivative of this was inverse tangent of x, right? That's what, and you asked, like, where is that written down? This is actually it. It just doesn't look like it is because I'm using u instead of x. And this formula, we can have any number here. So imagine a was 1. Imagine a was 1. You could write this way. So instead of writing du, I'm writing dx, and I'm moving it to the side. And then I'm putting 1 over 1 plus, instead of u, I'm using x. Do you see that this right here is that?
Yeah.
And then the antiderivative would be arctangent of x. Replace a with 1, like I did here. And do you see that that's the same answer?
So,
Just replace a with 1, and that's 1, and then that's u over 1, so that just becomes u. Well, all I'm telling you is that we have, these formulas are here, all right? Not ready to dive too deep into these, but I'm not going to say write them down somewhere else because we actually do have them. There's actually the more powerful general formula for it is here. Yes?
So that a can be any number as long as they all match the same number. Like
As long-
it always has to be whatever number for that one.
So like,
Kind of like x, it can be the same thing.
let's say that was a 4. Then a would be 2. But we haven't gotten here yet. But that's the way that formula would work. Here, a would be 2, and u would be x. So you'd replace that with x, that with 2, that with 2, you'd be done. All right. So we've already seen the power rule for finding antiderivatives, right? We've already seen the power rule. Basically says that if we're trying to find the antiderivative of x to a power, we use the power rule, this rule, whenever n isn't -1, and then when n is -1, it's the natural log of absolute value of x. So that's the same thing we just did, just written with different notation. Then we also know the common antiderivatives. Those are the ones, page 6 of your formulas 1 through 20. That's what I'm talking about here, formulas 1 through 20. These we will become more comfortable with. It says you should become comfortable. It's going to take us some time to get comfortable with these formulas, all right? But just know right now they're there, and I'll be referring to them as we proceed, all right? All right. That's the beginning, right? So I'm thinking about how I want to address this, or how I want to start this out. When it comes to like x to a power, sums and differences, adding and subtracting, we're trying to find antiderivatives. Everything is pretty straightforward. We have formulas for it, right? But things can quickly become very complicated because we also have multiplication and division, things like that. So we want to figure out, how do we find antiderivatives of more complicated expressions? Now in Cal 1, we had rules, didn't we? We say, hey, if we run into a product, we're just going to do the product rule. If we run into a quotient, we're just going to do the quotient rule. If we run into composition, we're going to do the chain rule. So in Cal 1 it is very, very mechanical, right? There's very much just a process. So here now, with antiderivatives, it just doesn't work that way. It just doesn't go backwards. There's no rules like that. There's these things we try. So the first thing that we're going to learn here for antiderivatives, or for integration, we're going to have these techniques, all right? And the first thing we're going to learn is called substitution. That's the first technique of doing integration is called substitution. More specifically, it's called U sub. If you were in my Cal 1 class, we did U sub. We started it, we got into it a little bit, right? All right, that's our first technique. Then the second thing we're going to learn is something called integration by parts, IBP. Integration by parts will be our second technique that we learn. A little bit of this will be on the first exam, just a little bit of it. Then we're going to learn about trig integrals. And when I say trig integrals, that means we're going to learn how to deal with integrals or antiderivatives when we have sine, cosine, tangent, secant, cotangent. Anything that involves trig, we're going to get some sort of technique to go after those. And then we're going to do this thing, learn this thing called trig sub, or trigonometric substitution. I'm just going to call it trig sub. All right, trig sub is interesting, to say the least. All right, we're going to learn that. And then after that, we're going to learn, what am I missing here? Partial fraction decomposition. I'm just going to put partial fractions.
So everything after 2 won't be on the first exam.
Everything after 2, yeah. Well, part of 2 will be on the first,
Right.
but a little bit of it, like the baby problems, like the beginner problems.
But not 3, 4, or 5.
Yeah, none of this will be on the first. This is going to take us weeks to do, all right? So that's the layout of the plan of where we're going to head right now in this class. And right now, for the remainder of this class, I'm going to see if I can get you to understand this concept here of U substitution. And I cannot stress to you enough how interconnected these are. Like there's no hope in doing 2, 3, 4, or 5 if you can't do 1. Like if you can't do this, you can't do that. Can't do that, can't do that. So everything is going to build on itself. And the problems we see here are going to make these look like baby problems, but you have to learn this first, all right, and get comfortable with it. So let's start with our first U sub problem, U substitution. And there's kind of a technique for this. There's kind of a technique. I'm not going to tell you the technique first, though. I'm just going to put a problem up, and then we're going to see if we can figure it out. So let's take a look at this.
What was that squared will be your U?
Oh, hold on. So look at the problem, and first, let's see why we can't use anything that we've already been using, like power rule, right? Why can't you use power rule? Because there's division, right? And because you have division, just like with derivatives, when you were in Cal 1 and you had a derivative, a quotient, did you just take the derivative of the top and bottom separately? No, you had to use a quotient rule, right? So with antiderivatives, finding the antiderivative of a quotient, it's the same thing. You can't just do the top and bottom separately. You're not allowed to. If that were the case, I always tell my classes this, if that were the case, Cal 2 would not be a hard class, okay? Because you just do top and bottom separately, you'd be happy and everything you'd go on with your merry way, right?
Is that not tangent inverse of x?
The answer to this would be tangent inverse of x if the 2x wasn't there. If that was just a 1 on top, our answer would be inverse tangent of x, because that would be something we remember from what we learned about inverse trig functions, right? They're derivatives. Yes?
Can you split it?
Okay, so yeah, so now the next question would be, if I can't do them top and bottom separately, right, can I split this into two fractions? Can you? Yes? Are you allowed to?
Yeah, because it's multiplication.
So how do you want me to split? I'm not sure, if you're going to say split, tell me how you can split that.
2x times 1 over bottom.
2x
Over 1 times.
times? Oh, split it like that. I got you. Oh, see. Sorry. That's not what I thought. What I thought was being suggested is that you do the 2x over 1 plus then the 2x over x squared. Like you split it into two fractions like that. Am I allowed to do that? Can't do that, right? Because you have, in order to do that, you have to have multiple terms in the numerator and a single term in the denominator. Then you can split, but you can't do it the other way around, right? So this is not okay. That's what I thought you meant when you said split. When I heard split. This I can do, right? This I can do. Now this is really just kind of like rearranging, right? I'm like factoring the 2x out the front. Now I have two things being multiplied, right? Can you find the antiderivative of each of those separately? No. In Cal 1, can you find the when you take derivatives of a product, do you do derivatives individually? No. So in Cal 2, you're not going to do antiderivatives individually either. You see? As much as you try and move things around and massage this and try and manipulate it, you're never going to get it to a nice, clean, easy thing that you can just do one at a time. All right? I thought I saw a hand.
Yeah. As far as like notation, after we start like dissecting or breaking it down or whatever,
Yeah.
we have to keep all the
Oh, yeah. We have to keep the symbols. I was listening to what people were saying about breaking down, so I was just doing like scratch work over here. Yes?
We just then make it, so for like 1 plus x squared, and make that like negative, to -1, so then.
You could write this as 1 plus x squared to the -1. That is correct. You could bring that up as that whole thing to -1. But then my question would be, what do you do with this? Because you still have two factors, right? These are factors. How do you find the antiderivative of a product?
Do the product rule with the antiderivative?
There's no rule, though. That's the thing. If there were a rule for doing antiderivatives of products, if there was a rule, I would give it to you. There is no rule. In calculus, right, in Cal 1, when you're taking derivatives, there is a rule, and it makes it it's not, I'm not going to say easy, but taking derivatives of products in Cal 1, there's at least a systematic approach, right?
So is this where you put in the substitution?
Yeah, so this is, what I'm trying to point out right now is there's nothing we have right now that allows us to deal with this. No matter how much massaging and rearranging and manipulating we do, there's nothing that's going to get us past the problem of a product or a quotient that we can handle, right? So, since there's nothing we can do, but we always have to look at that first, right? We have to say, is there anything we can do? Like, what if this problem was the other way around? What if it was this? Could you handle that? How?